Hello, my dear students. I welcome you all for this lecture. Okay, so that is the chapter number 13, Nuclei. Okay, in chapter number 12, Atoms, discussed in previous videos. There you have studied the Rutherford experiment, after that, Bohr's atomic model, and de Broglie explanation for the atom. So, according to the previous chapter, the atom is having the nucleus is in center. Almost all mass is concentrated in center and the electrons are revolving around the nucleus and that are the fixed orbits. In fixed orbits the electrons are revolving and the empty space is present in atom. Okay, some empty space is also there in atom that you are studying previous chapter. So today we'll start the chapter number 13, Nuclei. There we'll see the introduction. So in this we'll see what is meant by the nuclear physics. So nuclear physics, it is the branch of physics which deals with the study of constituents and the properties of nucleus. Okay. So what is meant by the constituents of an atom? So constituents of atom means electrons, protons and neutrons. Okay, the atom is constituents of the electrons, protons and neutrons. Then what is meant by the constituents of nucleus? So constituents of nucleus is the protons and neutrons. So protons and neutrons together they are known as constituents of nucleus. And what is meant by the nucleons? So protons and neutrons together they are known as nucleons. So here the atom, the constituents of atom is having electrons, protons and neutrons. Constituents of nucleus is protons and neutrons and nucleons are having the protons and neutrons. So we'll see the what is meant by the atomic number, that is Z. So it is denoted by Z. So atomic number Z, it is the total number of protons in the nucleus. Okay, it is the total number of protons in the nucleus, or it is also the total number of electrons. Okay, so the total number of electrons, or it is a total number of protons in the nucleus, that are known as the atomic number and that is denoted by Z. So next one is the mass number and that is denoted by A. It is the total number of nucleons. Okay, so total number of nucleons are known as the mass number. And the neutron number, that is A minus Z. It is the total number of neutrons in the nucleus. Okay, the total number of neutrons in the nucleus. So that is A minus Z. So it is the mass number minus atomic number. Okay, the subtraction of these two, mass number and atomic number, are known as neutron number. Okay, then we'll see the properties of nucleus. Okay, the first one, that is the nucleus contains neutron and proton. So nucleus is having the protons and neutrons. So and it is having the charge of nucleus as a plus Ze, where the Z is what? The Z is a atomic number and Next one, that is the radius of nucleus. R is equal to R naught a raised to 1 by 3, where R naught is 1.2 into 10 raised to minus 15 meter. And the density is independent of mass number, and the volume of a nucleus is proportional to the mass number A. So phi is equal to 4 by 3 pi r naught cube A, where when phi increases, phi means the volume of the nucleus. When volume of the nucleus increases, mass number is also increases. When volume of the nucleus is decreases, mass number is also decreases. So the V is directly proportional to A, where the P volume of a nucleus is directly proportional to mass number A. So next, that is a isotopes. So what is meant by the isotopes? Isotopes, it is having, the nuclei is having the same atomic number Z but different mass number A. So here for these examples, one hydrogen 1, one deuterium 2. Okay, so in this, the here the same atomic number, Z number is same, but the different mass number. So A number is having different. So for hydrogen it is 1, and for the deuterium it is 2. Okay, so it is having the different A number but same Z number. So next, that is a isobars. The isobars, the nuclei is having the same mass number A but different atomic number Z. So that are known as isobars. So for example, 32 germanium 76 and 34 selenium 76 are known as isobars. So here it is having the same mass number A but different atomic number Z. Next, that is a isotones. What is meant by the isotones? So isotones are the nuclei having same number of neutrons, and that are known as the isotones. So for example, the 17 chlorine 37 and 19 potassium 39. So here the 37 minus 17 and 39 minus 19. So both are having the answer as a 20. So therefore it is having the same number of neutrons. So same number of neutrons. So that is having the 20 as the same number for this example. Okay. Then the mirror nuclei. The nuclei with the same atomic mass, or that is a capital A, but with the proton and neutron number interchanged. Okay, the nuclei with same atomic mass A but with proton and neutron number interchanged. For example, 4 beryllium 7 and 3 lithium 7 are the mirror nuclei. Okay, so nuclei is having same atomic mass A value will be same, but with proton and neutron number interchanged. So that is known as the mirror nuclei. So these are Mirror nuclei are the nuclei that are having the same mass number but with interchange of proton number and neutron number. Okay. Next, one atomic mass unit is equal to, so the value of the one atomic mass number is equal to, that is 1.66 into 10 raised to minus 27 kg, and the energy equivalent of one atomic mass unit is 931.5 mega electron volt. Okay, so that is energy of the one atomic mass unit is 931.5 MeV. Next, that is the density of a nucleus. So the density of nucleus is 2.29 into 10 raised to 17 kg per meter cube. Okay, that is 2.29 into 10 raised to 17 kg per meter cube. And the mass defect. So what is meant by the mass defect? So mass defect is a difference between the sum of masses of the nucleons and the mass of the nucleus, that is known as the mass defect. So here the nuclear mass is equal to masses of all protons plus masses of all neutrons, and the masses of all protons as a ZMP, and masses of all neutrons is A minus Z Mn. Okay, so therefore the Z is what? That is a atomic number, A is a mass number, M is the rest mass of nucleus, and Mp is the mass of the proton, and Mn is the mass of the neutron. So difference between the sum of the masses of the nucleons and the masses of the nucleus, that is known as what? The mass defect. Okay, and that is denoted by delta M. Next, that is a binding energy. It is the energy required to break up the nucleus into its constituent particles. So where the binding energy Eb is equal to delta M into C square, where the delta M is a mass defect and C is a velocity of the light in vacuum medium. Then what is the relation between the binding energy, mass number, and binding energy per nucleons? So the EBA minus EB divided by A, where EBA is the binding energy per nucleon. Okay, so that is EBN is a binding energy per nucleon, or it is a specific binding energy. EB is a binding energy and A is a mass number. Then we'll see the binding energy curve and its features. So in this graph, we'll see along x-axis the mass number A, and along y-axis, that is the binding energy per nucleon mega electron volt. Okay, MeV. So here if you will see this graph, okay, so here the binding energy per nucleon is very low for the light nuclei. So initially it is very slow, and after that the binding energy per nucleon of both light and heavy nuclei is very low. Okay, for heavy and light nuclei it is very low, and the binding energy per nucleon increases rapidly up to A is equal to 20, and the curve contains the peaks corresponding to the helium, beryllium, carbon, and oxygen. The peaks indicates that these elements are more stable form with their neighbor like lithium, boron, and nitrogen. Okay, lithium, boron, and nitrogen. So like this, the binding energy per nucleon is maximum at 8.75 mega electron volt per here. It is very maximum, and hence it is stable, most stable in that region. And after that, the binding energy per nucleon of nuclei is having the mass number ranging from 30 to 170 nearly maximum value, and it is having the some significance also. The significance of a binding energy curve is what it gives the information about the stability of element, and it gives the binding energy of heavy nucleus, and that is low, and then the idea is used in nuclear fusion. Binding energy of a light nucleus is low. This idea is used in nuclear fusion. Like this, it is having the binding energy curve. Thank you.